Here's the problem about the pool light and the critical angle for total internal reflection. So you have an LED in the bottom, or not in the bottom, in the wall of a pool. There's the pool, here's the water, like that. Light in all directions. So we have rays coming up like this, we have rays going like that, we have rays going like that. And this is 1.6 meters here. There you go, it's 1.6 D. So this was the idea. It's going down as well. Let's see, so first, what is the critical angle for these rays? So remember, the critical angle is the biggest, the smallest angle of incidence that will still exit the pool. So, edit that out. So this ray, we know that if we draw the normal, the rays flee from the normal. And this ray, we know if we draw the normal, the rays flee from the normal. But we know eventually, if we draw a normal, they run out of angle to flee, and you get this effect called total internal reflection. And the ray doesn't go straight or down, it reflects according to the law of reflection inside the pool. So we draw something like that. So here, this was a really small angle of incidence, bigger. Eventually it reaches a size, this is as small as it can be, where it would escape the pool. And if it's bigger than this, it would go through total internal reflection. So the critical angle, we could derive it again, we don't really want to. It's where you set this refracted angle equal to 90, and you end up finding that it's the critical angle is the inverse sine of 1 over the index of the medium that you're in, the high index medium. So here in water, you're at 1.33 into air. So you have to be in a high medium and going towards a low medium to even have total internal reflection. So we would put 1 over 1.33. If you get them flipped over, your calculator will tell you that you're wrong because it has to be less than 1. Solve that and you get 48.75 degrees. So that's the answer to part A, 48.75. The critical angle defined in the normal way between the angle of incidence, or the normal and the angle of incidence. Let's see, the second question is, what is the smallest angle that will escape? And here, I didn't write all the words here, but it's the angle from the LED. So it exactly says, for light rays that escape the pool, what is the smallest angle between the light rays and the normal to the LED surface? So there it is. Okay. So here you can see rays that escape the pool will get smaller and smaller as you approach this critical angle. We're talking about this angle now. And eventually at the critical angle will be the critical case. Okay. So what is that angle when we're at the critical angle? Well, what you're supposed to recognize here is that these two, and I wrote the answer in the way, make a right triangle. Remember, geometrical optics is mostly geometry, not a lot of physics in it. So here you're just supposed to notice that those two normals are perpendicular. So if that is 48.75, then it must be a right triangle. Therefore, 90 equals 48.75 plus, we'll just call this theta wall, theta W. So the answer to part B is just 90 minus 48.75, which is 41.24, depending on how you round. Okay. And C, what is the distance they escape? So if you imagine what this will look like, it'll be like a circle of water where light is coming out here and it's not going out here. It's kind of like a circle. So the distance they escape is here. Like how far along the pool will they get out? And again, you're looking for right triangles here. There's your right triangle. And you know this theta, and you can do the geometry however you want. You can say, well, this angle of the right triangle must be 90 minus theta water that we defined, the theta inside the water. Or you could say this angle is equal to that angle, right? Because you have parallel lines and a line going between them. So there, then, that's theta water. So then you could say the tangent of this angle is opposite over adjacent. And adjacent is what we're looking for, x. So the tangent of, the tangent of 41.24 is opposite, which was the 1.6 over x. Right? So it's just a little bit of trig to get the answer to this one, and x is 1.825 meters. So now you know all the angles, you know how far out the light will